From the sidewalk, a skyscraper looks like one of the most rigid objects humans have ever built. Steel, concrete, glass, hundreds of feet of structure, apparently locked in place. But if you go high enough inside one on a windy day, that enormous building may be moving, not because something has gone wrong, but because it was designed knowing that it would. High-altitude engineering centers on the ability to manage this motion. The goal is to allow a structure hundreds of meters tall to flex and sway without that movement ever becoming perceptible to the people inside. To see why this is necessary, we have to look at how wind actually hits a building. It doesn't arrive as one perfectly steady shove. As air flows around a tower, it separates from the sides of the building, creating alternating, rotating regions of air in its wake. These are called vortices. As these vortices form and break away from alternating sides, the pressure changes. So instead of only pushing the tower directly downwind, the airflow produces a repeating sideways force, pushing and pulling the structure laterally. Every structure has natural ways it prefers to vibrate. If the wind keeps feeding energy into one of those natural rhythms, each push adds to the previous movement. That causes the sway to build up to dangerous levels. Engineers have to keep this response within strictly acceptable limits. The building has to safely resist the physical load, of course. But people are highly sensitive to acceleration. If the tower moves too much, occupants will experience discomfort, anxiety, and even problems with their balance long before the steel and concrete are ever at risk. So engineers attack the wind problem in layers. The very first layer of defense is the shape of the skyscraper itself. By modifying the building's exterior profile, they can disrupt the wind before the structural frame even has to deal with it. Take the Burj Khalifa. At over half a mile tall, its Y-shaped plan and varying setbacks are designed so that the building's width and geometry repeatedly change as it rises. By presenting a different shape at each tier, the architecture makes it incredibly difficult for wind vortices to organize consistently along the tower. The 632-meter Shanghai Tower tackles the exact same problem by twisting as it rises. Its outer form rotates about 120 degrees from bottom to top. By refining that geometry, engineers reduce the wind loads on the building by about 24% compared to early designs. These silhouettes are functional components of the wind control system. Their geometry is engineered to confuse moving air, neutralizing the physical problem before it can reach the internal skeleton. But changing the shape doesn't make the wind disappear completely. The forces that remain have to go somewhere, and that brings us inside the building to the structural frame. Many high-rises rely on a massive central concrete core to carry the weight. However, there's a structural limitation. If you try to stop a tall, narrow object from bending while only holding it near the center, you don't have much leverage against extreme lateral force. To gain that leverage, engineers use systems called outriggers. They extend horizontal structural ties from the central core and connect them to massive columns much farther out on the building's perimeter. These outriggers allow the core and those distant exterior columns to work together. Instead of one narrow spine resisting the wind by itself, the overturning force is distributed across the entire width of the building, creating a single, unified resisting system. Yet, even with an aerodynamic shape and a deeply unified skeleton, slender towers are still going to move. To manage that residual motion, skyscrapers start hiding massive internal machinery. Near the upper levels of Taipei 101, there is a suspended steel mass weighing roughly 730 tons. When the wind makes the skyscraper move, this tuned mass damper is engineered to respond differently, swinging in opposition to the tower to counter its response and dissipate energy. Not every damper uses a giant steel ball. In Philadelphia, the Comcast Center hides a tuned liquid column damping system near its roof. As the building moves, the motion of roughly 300,000 gallons of sloshing water is engineered to help absorb kinetic energy and counter the tower's sway. Similar specialized systems are hidden near the top of New York's Bloomberg Tower. The physical problem is always the same. Wind keeps putting energy into the structure, and these dampers exist solely to keep wind-induced acceleration at upper levels under control. Of course, you cannot build a 600-meter tower just to see if the occupants hate the motion. So before construction ever begins, engineers build meticulously detailed scale models and test them inside boundary layer wind tunnels that reproduce the exact characteristics of natural wind. The surrounding miniature city redirects airflow and changes pressures, revealing exactly how the real building will respond. If the test results are poor, the building's orientation, structure, or damping systems are altered. The final skyscraper is a direct, calculated response to an invisible fluid moving around it. When you put all of these hidden systems together, they function precisely in sequence. The aerodynamic shape confuses the wind to reduce the initial force. The structural skeleton spreads and carries the forces that remain. And the massive internal dampers remove the residual energy from any flexing that still gets through. All of these overlapping layers lead back to one very ordinary requirement: the human being inside. A person standing beside a window should be able to look out and treat a floor hundreds of feet in the air almost as if it were sitting directly on the ground. That absolute stillness is the front stage experience. It is a carefully engineered illusion that completely masks the fact that thousands of tons of steel and concrete are continuously negotiating with moving air. Skyscrapers endure extreme weather by embracing movement. By managing how a tower sways, engineers maintain structural integrity while ensuring the experience inside remains perfectly still.